We will understand in this class the classification of electromagnetic radiation, and will identify the thermal radiation as one of the electromagnetic radiation. This is going to be very interesting considering a lot of the things we see in nature are largely influenced by the understanding. I mean, it's all about electromagnetic radiation, so your understanding on the electromagnetic radiation is going to heavily help you. From your mobile phone to anything that you see in a heating element or something like that, even anything you see is basically the visible electromagnetic radiation. We'll further understand the idealized black body, the definition of black body, and we will calculate the total and spectral black body emissive power, calculate the fraction of radiation emitted in the specific wavelength band using the black body radiation functions, understand the concept of radiation intensity, and define spectral directional quantities using the intensity. We will also develop a clear understanding of the properties like emissivity, absorptivity, reflectivity, and transmittivity on the spectral and total basis. We'll be using Kirchoff's law to determine the absorptivity of a surface when its emissivity is known. We will model the atmospheric radiation by the use of an effective sky temperature and appreciate the importance of the greenhouse effect. The hot object in vacuum chamber will eventually cool down and reach the thermal equilibrium with its surroundings by a heat transfer mechanism, which is called radiation. So radiation differs from the conduction and convection, which you already studied in the last chapter, in that it does not require the presence of a material medium to take place. So the only difference, or the difference between the conduction or convection, is that this two method of heat transfer requires a medium, whereas radiation do not need any medium. Radiation transfer occurs in solid as well as liquids and gases. Accelerated changes and changing electric currents give rise to electric or magnetic field. These rapidly moving fields are called electromagnetic wave or electromagnetic radiation, and they represent the energy emitted by the matter as a result of changes in the electronic configurations of the atoms and molecules. The electromagnetic wave transport energy just like other waves, and they are characterized by their frequency and wavelength. These two properties in a medium are related by lambda equals to C by V. So basically, the definition of electromagnetic radiation is actually cited here. And this means that electromagnetic wave has a frequency and wavelength. And it is actually linked with the speed of propagation of wave at that medium. It has proven useful to view electromagnetic radiation as a propagation of a collection of discrete packets of energy called photons or quanta. In this view, each photon of frequency n is considered to have an energy of h nu, which can be also put as hc by lambda. The energy of a photon is inversely proportional to its wavelength. The type of electromagnetic radiation that is pertinent to heat transfer is the thermal radiation, emitted as the result of energy transition of the molecules, atoms, and electrons of the substance. Temperature is a measure of the strength of these activities at a microscopic level, and the rate of thermal radiation emission increases with the increasing temperature. Thermal radiation is continuously emitted by all matter, those whose temperature is above absolute zero. Everything around us constantly emits thermal radiation. So if you think about the electromagnetic spectrum, the thermal radiation is actually somewhere in the infrared and partially in the visible range. So that is why you have night vision cameras are also called infrared or thermal vision cameras. Light is simply the visible portion of the electromagnetic spectrum that lies between zero point 0.4 to 0.76 micrometers. And it has all these 7 colors. The radiation emitted by bodies at room temperature falls into the infrared region of the spectrum, which extends from zero point 0.7 to 100 micrometers. The ultraviolet radiation includes the low wavelength end of the thermal radiation spectrum and lies between the wavelength of 0.01 and zero point 0.4 micrometer. The ultraviolet rays are to be avoided since they can kill microorganisms and can cause serious damage to humans and other living beings. About 12% of the solar radiation is ultraviolet. The ozone layer is atmospheric, acts as the protective blanket, and absorbs most of this ultraviolet radiation. Most of this you already know. A body that emits the radiation in the visible range is called light source. The sun is our primary light source. The electromagnetic radiation emitted by the sun is known as the solar radiation. Almost half of the solar radiation is light, whereas the rest, ultraviolet and infrared. In heat transfer studies, we are interested in the energy emitted by bodies because of their temperature only. Therefore, we limit our consideration to thermal radiation. We'll not be studying other forms of electromagnetic waves in this. We'll just dealing with the thermal part of it. The electron, atom, and molecule of all solids, liquids, and gases above absolute zero temperature are constantly in motion, and thus radiation is constantly emitted, as well as being absorbed and transmitted throughout the entire volume of the matter. This radiation, that is why, is a volumetric phenomena. Let's get into black body radiation. Different bodies may emit different amount of radiation per unit surface area. A black body emits the maximum amount of radiation by the surface at a given temperature. It is an idealized body to serve as a standard against which the radiative properties of the real surfaces may be compared. A black body is a perfect emitter and absorber of radiation. A black body absorbs all incident radiation regardless of the wavelength and direction. So in general, the definition of black body is important because considering black body or irrespective of black body, all other bodies or other thermal phenomena will be described. So a black body is a perfect emitter and absorber of radiation. The radiation energy emitted by a black body is given by this equation. which also has the Stefan Boltzmann constant. Spectral black body emissive power. The amount of radiation energy emitted by a black body at a thermodynamic temperature T per unit time per unit surface area and per unit wavelength about the wavelength lambda is given by this equation. This is called the Planck's law. If you draw that against the wavelength at which the peak occurs for a specific temperature is given by Wien's displacement law. And it follows this law, which is the lambda T max power is equal to this. So from this equation, considering the multiplication at the maximum, which is the peak of this graph, if you know lambda, then you can figure out T. And if you know T, then you can figure out lambda. It's expected that you will be having numerical problems from this kind of a graph. From this figure, you can see the emitted radiation is a continuous function of wavelength. At any specific temperature, it increases with wavelength, reaches a peak, and then decreases with increasing wavelength. At any wavelength, the amount of emitted radiation increases with increasing temperature. As temperature increases, the curve shifts to the left to the shorter wavelength region. Consequently, a larger fraction of the radiation is emitted at shorter wavelength at higher temperatures. The radiation emitted by the sun, which is considered to be a black body at 5780 K, reaches its peak in the visible region of the spectrum. Therefore, the sun is tuned with our eyes. On the other hand, the surfaces at less than 800 K emits almost entirely into the infrared region and thus are not visible to the eye unless they reflect light coming from other sources. On an energy lambda chart, the area under the curve for a given temperature represents the total energy emitted by the black body at that temperature. The radiation energy emitted by a black body per unit area over a wavelength band from lambda equals to 0 to lambda is given by this equation. The black body radiation function is also defined by the fraction of radiation emitted from a black body at a temperature T in a wavelength band from lambda 0 to lambda by this equation, which is the radiation energy emitted by the black body per unit area by this value. The graphical representation of the fraction of radiation emitted in the wavelength band from lambda 1 to lambda 2 is given by this. The black body radiation function or some typical values are given here. Radiation intensity. Radiation emitted by all parts of a plane surface in all directions into the hemisphere above the surface, and the directional distribution of the emitted or incident radiation is usually not uniform. Therefore, we need a quantity that describes the magnitude of the radiation emitted or incident in a specified direction in space. This quantity is radiation intensity. We also need to understand the concept of solid angle. Though most of this will be covered in the mathematical course, a typical differential solid angle is given by this kind of an equation or a form for a differential area ds on a sphere of a solid r. Note that ds is normal to the direction of viewing since ds is viewed from the center of the sphere. In general, the differential solid angle subtended by a differential surface area dA when viewed from a point at a distance r from dA is expressed as this. Small surfaces viewed from the relatively large distances can be approximately treated as a differential area in solid angle calculations. For example, the solid angle substance atom is given by this. Now, with the knowledge of solid angle, the radiation intensity for emitted radiation is defined as the rate at which the radiation energy is emitted in the theta phi direction per unit area normal to the direction and per unit solid angle about this direction. The radiation flux for emitted radiation is emissive intensity. The rate at which the radiation energy is emitted per unit area of the emitted surface, which can be expressed in differential form. Noting that the hemisphere above the surface intercepts all the radiation rays emitted by the surface, the emissive power from the surface into the hemisphere surrounding it can be determined by integration. The intensity of the radiation emitted by the surface in general varies with direction, especially with the zenith angle theta, when many surfaces in practice can be approximated as being diffuse. Diffusivity emitting surface goes down to pi, i.e., considering this mathematical equation. So in case of a black body, it becomes only pi IB, where EB is the black body emissive power. So for black bodies, the IB becomes this. All surfaces emit radiation, but they also receive radiation, emitted or reflected by other surfaces. The intensity of incident radiation is defined as the rate at which the radiation energy is incident from theta phi direction per unit area of the receiving surface normal to the direction and per unit area solid about this direction. The radiation flux incident on a surface from all directions is called irradiation. Therefore, irradiation represents the rate at which the radiation energy is incident on a surface per unit area of the surface when the incident radiation is diffuse, and thus the diffusively incident radiation G is given by this equation, where the it's basically pi multiplied by the incident radiation. So another definition of the radiosity. The surfaces emit radiation as well as reflecting it, and thus the radiation leaving the surface consists of the emitted and the reflected components. So the quantity, if we define the rate at which radiation energy leaves a unit area of a surface in all directions, is called radiosity. There is also another definition of the spherical or spectral intensity for the emitted radiation, can be defined as the rate at which radiation energy is emitted at a wavelength lambda in the theta phi direction per unit area normal to its direction, per unit solid angle about this direction, and can be expressed by this. Then the spectral emissive power becomes this. We'll not go into too much of the mathematical jargons, but basically the spectral intensity of radiation emitted by a black body at a thermodynamic temperature T at a wavelength lambda is determined by the Max Planck by this equation, 1228. If you put on all these values, you basically get the other equation. The integration of the spectral quantity for all wavelength gives the total quantity. Let us now talk about radiative properties. Most materials encountered in practice, such as metals, woods, bricks, are opaque to thermal radiation, and radiation is considered to be surface phenomena for such materials. Radiation through semi-transparent materials such as glass, water cannot be considered to be surface phenomena since the entire volume of the material interacts with the radiation. A black body can serve as a convenient reference to describe the emission and absorption characteristic of real surfaces. That brings us to the definition of emissivity, the ratio of the radiation emitted by the surface at a given temperature to the radiation emitted by the black body at the same temperature. Emissivity is the measure of how closely a surface approximates a black body. The emissivity of the real surface varies with the temperature of the surface as well as the wavelength and the direction of the emitted radiation. The emissivity of a surface at a specific wavelength is called spectral emissivity. The emissivity in specific direction is called directional emissivity, where theta is the angle between the direction of the radiation and the normal of the surface. This is how we define the spectral directional emissivity, total directional emissivity, spectral hemispherical emissivity, total hemispherical emissivity, and which finally brings us to the ratio of the total radiation energy emitted by the surface to the radiation emitted by the black body of the same surface area at the same temperature. In case we have an actual variation of emissivity, like this function, it can be approximated by a step function that can be calculated mathematically. A surface is said to be diffuse if its properties are independent of the direction, and gray if its properties are independent of wavelength. The gray and diffuse approximations are often utilized in radiation calculations. The comparison of the emissivity and the emissive power of a real surface with those of the gray surface and the black body in the same temperature is actually defined here. The variation of normal emissivity with wavelength and temperature for various material is also given here. The typical ranges of emissivity for various materials you can see from this picture. The radiation analysis, it is common practice to assume the surface to be diffuse emitter with an emissivity equal to the value of normal theta equals to 0 direction. The definition of absorptivity is the absorbed radiation by the incident radiation. Reflectivity is the reflected radiation by the incident radiation. Transmitted radiation and the incident radiation gives us the transmittivity. Irradiation is defined by the radiation flux incident on a surface. The absorptivity, reflectivity, and transmittivity combined gives us the radiation. The total value of absorptivity, reflectivity, and transmittivity is basically 1. This may not be something we want to cover now, which is spectral hemispherical absorptivity and all that. In practice, surfaces are assumed to reflect in perfectly specular or diffuse manner. The angle of reflection equals the angle of incidence of the radiation beam is called specular reflection. Diffuse reflection is radiation is reflected equally in all directions. Kirchoff's law is quite an important one. The small body content in a large isothermal enclosure used in the development of Kirchhoff's law, which is given by the total hemispherical emissivity of a surface at a temperature T is equal to its total hemispherical absorptivity of the radiation coming from the black body at the same temperature. The emissivity of the surface at a specified wavelength, direction, and temperature is always equal to its absorptivity at the same wavelength, direction, and temperature. The greenhouse effect. Glass has a transparent window in the wavelength range from zero point 0.3 micrometers to 3 micrometers, in which over 90% of the solar radiation is emitted. The entire radiation emitted by the surfaces at a room temperature falls in infrared region, which is greater than 3 micrometers. Glass allows the solar radiation to enter but does not allow the infrared radiation from the interior surfaces to escape. This causes a rise in the interior temperature as a result of energy built up in the car. This heating effect, which is due to the non-Greek characteristic of a glass or clear plastics, is known as greenhouse effect. In case of atmospheric or solar radiation, the radiation energy emitted or reflected by the constituents of the atmosphere is called atmospheric radiation. The energy of the sun is due to the continuous fusion reaction, during which two hydrogen atoms fuse to form one atom of helium. Therefore, the sun is essentially a nuclear reactor, with temperature as high as millions of K in its core region. The temperature drops to about 5,800 K in the outer region of the sun, called the convective zone, as the result of the dissipation of this energy by the radiation. The concept of solar constant you may be hearing later. The total solar irradiation. It represents the rate at which the solar energy is incident on the surface normal to the sun's ray at outer edge of atmosphere when the Earth is at its mean distance from the sun. The sun can be treated as a black body at a temperature of 5,780 K. The spectral distribution of solar radiation just outside the atmosphere at the surface of the Earth on a typical day, in comparison of the black body radiation is 5,780, will match quite close. That is why the sun can be treated as a black body at a temperature of 5780. The spectral distribution of solar radiation on ground plotted in this figure shows that the solar radiation undergoes considerable attenuation when it passes through the atmosphere as a result of absorption and scattering. About 99% of the atmosphere is contained within the distance of 30 kilometers from the Earth's surface. The several dips on the spectral distribution of the radiation of the Earth's surface are due to absorption by the gases, oxygen, ozone, water, and carbon dioxide. The absorption by oxygen occurs in narrow bands, about zero point 0.7 micrometers. Ozone, ultraviolet radiation, below zero point 0.3, and the radiation in the range of zero point 0.3 to zero point 0.4 considerably are reduced by this, I think. Thus, the ozone layer in the outer region of the atmosphere protects the biological systems on Earth from harmful ultraviolet radiation. In turn, we must protect the ozone layers from destructive chemical commonly used in refrigerators, cleaning agents, and propellant in aerosol cans. As a result of this absorption, the solar energy reaching the Earth's surface is weakened considerably. The solar energy incident on a surface of Earth is consists of direct and diffuse parts. It is found convenient in radiation calculations to treat the atmosphere as a black body at some lower fictitious temperatures that emits an equivalent amount of radiation energy. The fictitious temperature is called effective sky temperature. The value of this temperature depends on the atmospheric condition. It ranges from about 230 K for cold, clear sky conditions to about 285 K for warm, cloudy skies. The absorption and emission of radiation by elementary gases such as hydrogen, oxygen, nitrogen at moderate temperatures are negligible. And a medium filled with these gases are treated as vacuum in radiation analysis. This absorption and emission of gases with a larger molecule such as water, carbon dioxide, however, can be significant and may need to be considered when considerable amount of such gases are present in a medium. For example, 1 meter thick layer of water vapor at a 1 atm pressure and 100 degrees centigrade temperature emits more than 50% of the energy that black body would emit at the same temperature. The radiation properties of a surface are quite different for the incident and emitted radiation, and the surfaces cannot be assumed to be gray. Instead, the surfaces are assumed to have two sets of properties. One, the solar radiation, the another one is infrared radiation at room temperature. What we call renewable energy is usually nothing more than the manifestation of solar energy in different forms. Such energy resources include wind energy, hydro, electric power, ocean thermal energy, ocean wave energy, and wood. Although solar energy is sufficient to meet the entire energy needed of this world, currently it is not economically to do so because of the low concentration of solar energy on Earth and high capital cost. It is very fast changing. So in this class, we have covered the introduction of the topic radiation, some idea about thermal radiation, black body radiation, radiation intensity, just got an idea about solid angle, intensity of emitted radiation, incident radiation, radiosity, spectral quantities, radiative properties like emissivity, absorptivity, reflectivity, transmittivity, and Kirchoff's law, the greenhouse effect, and atmospheric and solar radiation.